We're now going to see how substitution works with definite integrals. We have the integral from 0 to the square root of pi of x times the cosine of x squared dx. As before, we have our substitution, u is equal to x squared. And so du is equal to 2x dx. So I can rewrite the integral. X times the cosine of x squared dx. And I know that I need a 2x dx, not just an x dx. You know, it might be easier to see what I'm doing if I actually put the x next to the dx. All right, there we are. And then I need to multiply and divide by 2. So I'm multiplying inside by 2 and outside by 1/2. And now I have a 2x dx. Now, in the last series of videos, I stopped writing the u substitution. But here we have limits of integration, and I need to make sure that I keep writing the limits of integration. Let me just pause for a moment and say why that is. You may recall that a definite integral has a result that's a number, and an indefinite integral has a result that's a function. And so if I don't write down the limits of integration, I've just changed this from a number to a function. I've changed what kind of thing it is, and that's not okay. A lot of people like to, I guess I'll call it efficient instead of lazy, but a lot of people like to leave off the limits of integration and then throw them in at the end. That is not right. That's mathematically incorrect. Now, when we have limits of integration, when we have a definite integral and we're using the substitution rule, we're going to substitute the variable out. So x squared gets replaced by u, so the cosine of x squared gets replaced by the cosine of u, and then 2x dx gets replaced by du. Now, the original limits of integration were x limits. You see, we had a dx, and so our variable of integration was x. Now, I need to change this. I'll use green. I need to change this so I'm in the same language here. My differential is du, and so I need to change my limits to u limits. And I think that a good visual for this is using a table. So x and u. And remember, our substitution is u is equal to x squared. So I'm actually going to write that in the table. U is equal to x squared here. And then the lower limit is 0. The upper limit is square root of pi. So I'm going to put those in the table in that order. 0 on bottom, square root of pi on top. And then, what values do these x values map to? Or I guess what u values do these x values map to? If x is the square root of pi, then u must be pi. If x is 0, then u is equal to 0 squared, so 0. I then write those new limits of integration. I've now done a change of variables. And that's something that I will do most of the time, if not all, when we have, I guess most of the time, when we have a definite integral. Change the limits over. Now I'm in the realm of u, and let's integrate. 1/2, the integral of the cosine is the sine, so 1/2 sine of u. At this point right here, I differentiate in my head. The derivative of the sine is a positive cosine, so I don't need a negative. We're good there. I don't write plus c because this is a definite integral. I'm going to evaluate from 0 to pi, and here we end up with 1/2 of the sine of pi is 0, the sine of 0 is 0, and the answer turns out to be 0. I want you to notice what I didn't do. What I didn't do is then bring this back into x in terms of x. That's a requirement for indefinite integrals. It's never a requirement for definite integrals. We change the limits of integration when we change the variables. And then for goodness sake, if it's a definite integral, don't go back to the original variable. People do that. I've seen it. They'll do this and they'll change the limits and then they change it back, and it's just a whole lot of extra work. Please be efficient and do it the way I showed you. Next, we have one that maybe will have you scratching your head a little bit. It's the integral from 0 to a of x times the square root of a squared minus x squared dx. And the only reason it might have you scratching your head is because we have this a in here. It's a constant. Just treat it like a constant. I know it's a constant for a couple of reasons. One, it's towards the beginning of the alphabet, and they tend to be constants. That's not hard and fast always, but we have dx here, which means that my variable is x. And this is single variable calculus, so I can only have one independent variable running around. I'd like for you to do this and then come back when you're done. Our substitution is u is equal to a squared minus x squared, so du is negative 2x dx. I went ahead and wrote down the change of limits. So 0 is the lower limit, a is the upper limit. But with our substitution, 0 maps to a squared and a maps to 0. Folks, those go in the exact same places, like positionally, that they were. So 0 maps to a squared, a maps to 0. I don't just randomly put the biggest number at top all the time. It matters what they map to. Now, yeah, there's that property of integrals that says I can flip the order here as long as I change the sign out front, but I didn't use that. Because my du has a negative 2 in front of x dx, I had to multiply and divide by negative 2. And then I'm really integrating the square root of u, or u to the 1/2. After using the power rule for integrals, and then evaluating at 0 and a squared, 0 gives me 0, minus a negative when I evaluate the a squared, I get 1/3 a cubed. How'd you do? Probably don't talk to the computer.